The next question is, what do you think is the most important outstanding problem in foundations of quantum mechanics? Markus, would you like to give a short answer?
I don't think I can answer this because everybody will have different views. My view is I would like, in general, to connect foundations of quantum physics in this quantum information perspective more with space and time, perhaps towards quantum gravity, not really quantum gravity, but yeah. But this is a matter of taste, I think. I don't feel qualified to tell the rest of the community what's the most important problem.
Right. Matt, first round of
I'm going to say things that need to be explained later, but solving the fine-tuning problem without throwing out all possibility of having explanations. That's the short version of...
Matt, would you like to elaborate on that?
Yeah, okay, so I mean, going back to the last question, the easiest way to solve the measurement problem, as was done, was by let's make a realist version of quantum mechanics from which we can explain what a measurement is and why there are definite outcomes and all this kind of stuff. And so that's what's been done. But we have all these no-go theorems, right? And the no-go theorems, things like Bell's theorem and the Quotient-Spurgeon theorem for contextuality, and even things like theorems about the reality of the wave function, I tend to view those in the context of thinking of them as fine-tuners. And so I've done some work on that. Speckens and collaborators have done some work on that, but it's in a bit of a different framework. But the basic idea is you prove that your underlying realist physical theory must violate some property that holds of the operational predictions. So in the simplest example is perhaps Bell, where you'd say something like this. You'd say, well, I can't send a signal operationally. So there's no signaling. There's no superluminal signals that can be sent using quantum mechanics. However, in the underlying physical theory, there are influences that are going faster than the speed of light. So why can't we use them to send a signal? That's only possible because basically the probabilities, what your uncertainty about the underlying state of reality, has to be set up in just such a way so that when you average over that uncertainty, the possibility of signaling gets washed out. Okay, and then there's lots of no-go theorems that are of this form. You can think of contextuality in this way. Contextuality says you have two things that there's no way of distinguishing them by any experiment operationally, and yet you prove that they must be represented differently. They must be different at the underlying physical level. And there are other things to do with time symmetry. So there's a whole host of these things. Now, are these things a problem? I mean, not necessarily. So there are various ways of getting out of them. So one way is to say, well, okay, we're just going to accept these things as facts. We've proved that this thing must exist. These things must happen. A theory like de Broglie-Bohm theory, for instance, does indeed have all these properties. There you go. Okay. That's one way of thinking about it. Another way of thinking about it is, well, these are reasons why you might want to reject those kinds of explanations, because we have all of these principles, which are symmetry principles and things like that, very useful for building the theory at the operational level, and we want to think of them as fundamental if we possibly can. So the challenge there is to say, well, okay, there must be something wrong with the framework in which we're proving these theorems, and so therefore something about the traditional realist framework that you use to prove things like Bell's theorem, etc., must be wrong. Okay, that's one way. and then we try to find a framework in which we don't have those kind of fine tunings. Another possibility is that the fine tunings are emergent, right? So this is, you would have, at the beginning of time, you wouldn't actually have these symmetries, but there's some dynamical process, which makes them appear, a bit like thermal equilibration. Now, I would accept that kind of explanation, and that's the kind of explanation that non-equilibrium de Broglie theory gives. But you have to be bold to accept that kind of explanation, because it means predicting that quantum mechanics will be violated in some quite extreme ways. Since we have no evidence for that right now, I'm not inclined to believe that that's necessarily the right kind of explanation, but it is a possible explanation which would be valid. So I'm more interested in saying, well, what's wrong with the current framework? And that means that we're going to have to give up on some things that are typically thought of as required for realist interpretation, something slightly more exotic. But the trouble is that, once you start giving up on things, you're like, well, I don't have a realist explanation, so what kind of explanation can I have? So, in a lot of Neo-Copenhagen interpretations, things like cubism, you give up an awful lot of explanations. So it's like, what is the explanation for the Bell correlations? Usually we would like to think that there's some kind of common cause explanation. That's exactly what Bell was trying to establish, whether it was possible. The source which emits the two particles, that should be the cause of the correlations that we observe. Now, you can't do that in a local way. The non-local theories deny that that's true. And even Copenhagen type theorists say, what they say about the situation is that we give up on explaining those correlations. Correlations just can be without a causal explanation. But we can also, again, Rob Beckens and I have worked on this kind of approach, try and come up with a sort of genuinely quantum notion of causality in which we do have a common cause explanation. Now, that thing is not unproblematic. It's not straightforwardly realist. It's given up on some aspects of realism in order to get there. But it seems like, oh, look, it is actually potentially possible to strike a medium ground here, where, we give up just enough to get rid of the fine tunings, but we don't give up all, we don't, throw out all of our explanatory tools. In particular, we're going to retain some notion of causality. Now, I'm not saying that the way that it is formulated now is necessarily the right one. I think we're still looking for that. But, that's what I mean when I say I want to solve the problem of fine tuning, but without throwing out all of our explanatory resources.
Marcus, is there anything you want to comment on? I know this is less of a debate than a discussion, but if you have something to say, please.
Yes. So, I do agree to a large extent with Matt that this fine-tuning problem is sort of at the core of the question how we should think of quantum theory. And so we have all these no-go theorems, which can be summarized as saying, here's a nice property at the operational level, for example, the causal structure or the mixture structure. And then Bell's theorem or non-contextuality theorems would tell you, oh, if there's an underlying level at the ontological level that follows, for example, Harrigan-Specken's ontological models framework, then it cannot have this nice property. So the causal structure must be different. So even if we can signal operationally, there must be signaling on the fundamental level. Or the mixing structure must be different. So things that I can distinguish as statistical mixtures ontologically are washed out and become indistinguishable at the operational level. So this is like the core insight of the no-go theorems. Now the question is, what do you do? What do you make of these no-go theorems? And part of the reaction, I think, a rational reaction is to say, well, then we must give up this ontological model. So to speak of like actual variables that underlie the state of affairs, the state of reality that sits there, must be wrong in some sense. Now, where to go from here? Well, that's necessarily a part of the speculation. Certainly, the way I interpret it is to say, well, some of these reason no-go theorems point in the most like intuitive way at a sort of perspectival view, perhaps, where outcomes and perhaps also the probabilities of these outcomes, if you want, pertain to the agent or are local and not for everybody in some sense. And but what I also would like to say is, like you asked me in the beginning, this great question, what I think is the most important problem in the foundations of quantum mechanics, and I wasn't really sure what to say. That has also to do with the fact that I believe that it would be fruitful to broaden the horizon a bit and to say let's not just do quantum foundations or just say work with what quantum theory tells us, try to interpret quantum theory full stop, but let's put this into a broader perspective. I'm not saying naively, like sometimes you hear, oh, maybe tomorrow we have quantum gravity, and then maybe this will solve our problems of the interpretation. I don't believe that, and that's not what I want to say. But it seems to me that there are other puzzles that have to do with, observations like, of agents in strange situations that I think I just want to consider in conjunction and together with these quantum puzzles. So that's certainly something, like my own like view on this, but I think it might help to put like this into context and to see what other puzzles of physics and philosophy, how they relate to this. And then this perspectival view where we say perhaps outcomes belong to observers. They are private in some sense. Whatever outcome means, whatever observer means, whatever probability means, that might be a hint that we want to have a picture that begins as its like fundamental element with the first person in some sense. Yeah, that's my what I personally take from that. Now that's just one possible direction to go, and I may be wrong in doing this, but that's something that I think is worthwhile. But there are other ways in which what Matt said is important. So thinking about how can fine-tuning move you from a classical level to something that averages out and that looks non-classical, I think that's a fascinating question. It's also practically relevant. So for us, for example, at the moment, it's relevant in something very concrete that we want to do. We want to say, for example, can we certify non-contextuality, like Speckhan's notion of contextuality, even in a quantum system in the lab, that we can do only very coarse measurements. We cannot do all the quantum measurements and probe it only with just a few of these measurements, very incompletely. Can we still infer that the system is not classical? And the answer to this question will depend on the ways in which seemingly non-classical data, things that look non-classical, can arise naturally from something underlying classical. So understanding more how this is possible or impossible can also, I think, inform these sorts of experiments and investigations. So yeah.
Yeah, I mean, let me add something to say. First of all, I do think you're right to say that we need to consider these things in conjunction with other puzzles. I mean, sometimes it's the case that in order to solve a problem, you have to look at it from sufficient altitude. That's to kind of like step back and say, okay, what's the broader picture here? The other thing I want to say, though, it's sort of related to what you're saying there, is a while ago in talks, I've never written this down, but I've sometimes asserted that I believe in a principle of minimizing weirdness. I was very flattered to Harvey Brown, before he retired, a philosopher of physics. He wrote a paper attacking his notion of minimizing weirdness, even though I'd never written it down, but I was very happy that he thought it was worth attacking. But the idea there is that we do have situations in which we know can be reproduced by classical theories like such as Speck's toy theory and things like that.
Yeah.
We have things like stabilizer, but we have situations in where, for example, if you look at the Wigner function, formalism, everything's positive and it behaves like a probabilistic local hidden variable theory, and no non-locality is required, no contextuality is required. And I say, wouldn't it be nice if our actual interpretation of quantum mechanics said that when no weirdness is needed, there is none? That would actually be highly explanatory, because then you could look to your interpretation of quantum mechanics and it would tell you which phenomena could possibly lead to quantum advantage, because surely situations where non-locality is not actually needed, if your theory said, yeah, those situations are perfectly local and it's only when we actually need non-locality that it comes in, that would be useful. And if we're sort of equating scientific truth pragmatically with utility to some degree, then clearly that would be a good thing to have. Now, our present interpretations of quantum mechanics are nothing like that. Many worlds says that whenever a measurement is made, we split into two worlds. It doesn't say whenever a measurement is made that cannot be explained by classical theory, we split into two worlds, right? And similarly, de Broglie theory is radically contextual and radically non-local. Like even standard EPR experiments that can be explained locally, you need Bell's theorem to have non-locality. But de Broglie theory says large amounts of non-locality going on even in the EPR experiment. So this is maybe another way of articulating why we might be skeptical of the current interpretations as they exist, because it would clearly, to my mind, be more explanatory if we could use the interpretation should be useful for identifying things that are interesting to look at. And currently, most of the interpretations just say crazy weird stuff is going on all the time, even in sort of situations which are highly classical. And that's not really, I mean, it provides an explanation in terms of, it's giving me an ontology and it's giving me a dynamics and it's like maybe solving the measurement problem, but it's not really working to explain much else. And that's I think we could do better.
Markus, before I ask you, the next question I'm going to ask is weirdness a valid criteria in judging scientific theories? With that in mind, Markus, do you have any comment on what Matt said?
No, because whatever I would want to say is probably coming up now anyway in the next question.
Okay. So here we go. The next question is, should weirdness be a criterion for judging the validity of scientific theories? Markus, please give a short answer.
Yes and no. That's my short answer. I think I have to say a few things about what I mean by that.
Okay. Then you have a chance in the next round.
Yeah.
Matt?
I'm going to say a similar thing. No, but it depends on what you mean by weirdness. You need to give a technical definition of weirdness, and I can answer that question.
Okay. Perhaps I'll ask Markus first to elaborate on his own answer.
Yes. So, before getting to the core of this question, first I want to say that I'm a big fan of this research program that Rob and Matt and others, Lorenzo, and have come up with this. You really are carefully analyzing which aspects of physics can be explained classically and which cannot. This is, I think, extremely valuable. It sheds so much light on quantum theory that it's immensely helpful. I mean, even back as a teenager, I remember reading all these popular scientific books, how interference is so mysterious, or wow, how can it be in an experiment with entangled particles that, oh, one of them measurements shows spin up, the other one must immediately show spin down. Well, I can do this with a pair of shoes, right? So it's immensely important and insightful to clarify exactly what can be reproduced classically and what not, for many reasons. One of them also is like it lets us understand how we can take advantage, or in which cases can we not take advantage of these quantum weirdness, if you want. So this is extremely important research. I'm not sure, however, that I would say that it's a sign of truth of a scientific theory if it's not weird. So especially if we say theories have to be intuitive, I think that's just not what happened in the history of physics, and it's against my personal taste either. Right? So general relativity, quantum theory, even evolution and whatnot, all these theories were extremely counterintuitive at first. So if we say things are not weird and they are intuitive, if the usual Homo sapiens, over lunch mumbles and hears that and thinks, well, that sounds pretty reasonable. Like, that's not a sign of truth, right? So I rather think that we should expect our theories to be counterintuitive, and especially if there's actual progress, I would guess that it typically comes with an approach or theory that is very surprising and counterintuitive first. So I don't think it's a virtue to not be weird, but it's certainly a virtue to be clear, to have clarity and economy of assumptions and of thought. But these do not go hand in hand with being intuitive, I think. So I'd be very happy to throw away the ontological models framework. And well, that's what I did. I proposed a way in which is very an approach which looks very extremely weird to begin with. But I would hold up other criteria much more highly, which is make as few assumptions as possible, be as concrete as possible in your assumptions. Can you write down mathematically, be very clear in the relation of that and the actual things we see in a lab as far as you can, right? Rather than not being weird. But weird can mean many things. So if weird means hard to understand even after you've worked with it for years, or weird means that it's just older authority people that tell you the theory. It looks weird to you, but haha, who are you? Like, we know what we do. So it should come with a lot of clarity, but not necessarily. It should not necessarily be intuitive, I would say. But that's yeah. I mean, the philosophers of science would have to say much more about the vices and virtues of physical theory. So this was more like a personal answer, like what motivates my own research, or what I find plausible or not, what I want to work with or not. No.
Good. Matt, in your short answer, you said one needs to give a technical definition of weirdness.
Yeah. Well, I mean, since a lot of us who study physics are nerds, I'm sure that we all grew up as being called the weird kids. So I can only say that from that perspective, being weird is good, right?
Agreed.
I mean, yeah, I mean, I mean, I agree with Marcus that if you talk about weird meaning counterintuitive, then of course scientific theories are going to be counterintuitive, at least when we first develop new ones. I mean, that's the whole point, right? So if our intuitions were always right, if common sense was always right, then we wouldn't really need formalized science, right? We need formalized scientific theories for understanding, that actually we have to do things in a systematic way, because actually our intuitions are often wrong. So I definitely agree with that, and the history of science just proves that to be right. Everything from the Copernican revolution to quantum mechanics, general relativity, all of these things, even Newtonian mechanics, right? Newtonian mechanics. It's amazing how many people talk about Newtonian mechanics as if it's intuitive, but the idea that sort of the natural state of something is to keep in motion if it's in motion at a constant velocity, just directly contradicts our intuition about how everything behaves on Earth. Okay, we know that's to do with friction and air resistance now, but it takes sort of a leap of imagination to think things that way. So all our theories of fundamental physics have always been counterintuitive, um, and so that will continue. However, when I'm talking about the weirdness of quantum mechanics, of course, in this kind of spec and program that I'm involved with, we kind of have a technical notion in mind, which is that something that can be reproduced in a classical theory of a certain type is not weird. I mean, in some sense, weird is not maybe the wrong word, but in some sense, that's what we mean by thing. Instead of weird, I would say maybe sort of genuinely non-classical in some way. And in that sense, as I sort of indicated in my previous answer, I think that there is some virtue to minimizing the amount of weirdness in that sense, the amount of non-classicality in the theory, because if you think that the idea of an interpretation of quantum mechanics is that it should provide better explanations than the ones that we currently have, then an interpretation that would help you to identify genuine non-classicality, as opposed to just saying things are highly non-classical all the time, I think would be more useful than one that isn't. Now things will still be weird because the counterpoint to this Beckons program is, yes, we've identified all these phenomena that occur in classical theories of a certain type, but it's usually only some aspects, right? So in the literature, people will say, oh, interference is weird because XYZ, the kind of paradoxes that Feynman talked about. And then we might say, no, you can reproduce those. But then you find there's some other aspect of interference, some more subtle aspect, like the trade-off between the degree to which you can tell which path the photon went down versus the degree to which you can observe interference. That precise trade-off may indicate non-classicality. So it's not that we're banishing the weirdness entirely. In fact, it's most definitely there, but it's there in more subtle ways. And so I would personally like to see an interpretation which is which indicates the subtlety with which the weirdness comes. Whereas, some of the interpretations that we have now appear to be sort of hitting on this weirdness like a sledgehammer, right? It's like, oh, it's always weird all the time, 100% of the time. And that to me seems like, well, those interpretations definitely look like they were sort of glommed onto the formalism afterwards, rather than sort of giving deep insights into the way things actually are.
Okay, Markus, it's your chance to speak. Don't forget that you're not limited to making statements. You can also raise questions directly to the other party. Markus.
Yeah. Yes, I think I feel like I made already too many statements. So why not let me ask a question to Matt? So, what's next? So, for you personally in this program, where do you want to go? I'm really curious about what you're planning to do, and so what do you think like all this is going?
Yeah, I mean, part of me is like, well, if I really knew the best direction to go, I would be doing it already, and I wouldn't be so uncertain about things. What I think is that there are a number of sort of roads less traveled, and it would be good to investigate them. I don't have a strong sense that they're necessarily right, or that one is necessarily much better than the other. So, I have been working for a while on theories that involve retrocausality. I am interested in developing further notions of genuinely quantum causality. But I think due to arguments by Eric Cavalcanti that it will have to be, causality is itself going to have to be perspectival in some way, right? So there's going to be some subjective notion of causality that comes in the quantum case. So those kind of things are interesting, but we may still get something from that. Otherwise, I don't really know. Is the bottom line. I don't have a strong idea. I think it's good that there are people investigating different kinds of approaches. I'm going to be theoretical physicists. We're just opportunists at the end of the day. You see where there's an interesting result. You see where there's an interesting new mathematical technique that might be applicable to things you're interested in, and you go and you try to do that. So we sort of do a random walk using our intuitions as to what's the best directions to go, and sort of bias it slightly this way or that way. I don't have a huge. I really shouldn't say this right now because I'm going up for tenure students, so they want to know that you have a very concrete vision. But in reality, we're all opportunists to some extent. I hope that there'll be the right ideas will sort of emerge over the next few years and decades, and that we'll make progress. I think we've been making progress so far. It's undeniable that we know more about the foundations of quantum mechanics than we did. However, a lot of what we know is negative stuff, and we need to, in the sense of it can't be like this, it can't be like that, it can't be like no-go theorems and such like. It would be good to try and develop the positive side of it in a way that is likely to be successful, not just sort of proposing something for the sake of proposing it, but sort of carefully trying to fulfill these ideas that I've talked about, like minimum weirdness. I mean, I have one idea that I have been working on. I don't think it's promising as a theory of reality, but with my postdoc, just as a sort of I guess just as sort of proof of principle, try to take the Wigner formalism and extend it into a hidden variable theory in such a way that it matches the Wigner function when everything's positive, but the dynamics that you've written down, as soon as something becomes negative, it reproduces that by introducing some non-locality or contextuality, but it matches the Wigner function otherwise. So we had some ideas about how to construct such a theory, and we're making some progress, but then everything turned out not to work. Well, I'm still thinking about ideas along those lines, actually, like trying to implement the idea of minimizing weirdness in a concrete theory. Yeah, so I mean that's just a few thoughts. I don't have anything really coherent. I mean, I would also love to hear how you want to develop your approach, particularly going towards an understanding of quantum mechanics, quantum probabilities themselves as well.
Yeah. So, I mean, I think before saying what I specifically want to do, I also feel, as you said, that there has been a lot of progress in the field. So we understand now so many things much better about the foundations of quantum theory. And perhaps there's some homework for us to be done to communicate this better. I feel like when I go in schools and talk about Bell's theorem, then people are really fascinated, some of them, right? And many of them have never heard of this sort of stuff. So they either read some esoteric books about quantum theory, or they read books about how string theory and extra dimensions explain everything. But I mean, perhaps perhaps you even, Matt, or some others are doing this even now successfully. I'm just not that aware of it. But we could communicate to the public a bit better what we found and how careful we've actually been working to prove actual theorems, and what we can say or we can say that we cannot say, right? So it's just such a fascinating body of insight that we have that I wish it would be appreciated more by the public, perhaps. Yeah, but this is like a general feeling For myself, I have a couple of things I do independently. Some of it has to do with Rob's notion of contextuality. Some of it has to do with reconstructions of quantum theory and asking how structure of quantum theory relates to space and time. But yeah, certainly there's still this approach that I'm having that I've tentatively called algorithmic idealism that we talked a bit about. Where all I want to do next is really explain its main idea in a few sentences in a way that's actually understood, because it got misunderstood a lot. I met Chris Fuchs recently, and Chris is very supportive, and he's in many ways of thinking about quantum theory very close to me. And then he told me that he thought I have this view that the world is just a Turing machine. And then I told him, Chris, no, not quite. It's a completely different thing. And that told me that I did something very wrong in how I perhaps tried to explain my main idea. So this gives me some homework, and that's the kind of homework I want to do now, in addition to the other things. So yeah, that's where I'm going at the moment, I would say. Yeah.
So I think I will refrain from getting into a huge critique of your work until I see. I think it'll be very helpful to see that stated in that kind of way, and also you'll probably get more productive interaction with the philosophy of physics community once we have that. So I'm looking forward to seeing that when he gets around to it. I have to say on your other point about communication, we haven't always been that great at communicating even with the rest of the physics community. And we haven't even been that great at communicating even with the community of quantum information and quantum computing people, even because, there are a large number of those, especially since the field has expanded so much into trying to practically build quantum technologies. There are a lot of people who sort of know very little about the foundational roots of these technologies. And even sort of, I've come across active hostility towards foundations from people within that field, which you wouldn't have expected so much. I mean, you expect it from the physics community as a whole. So, I think we could do better communication on all levels. It includes things like textbooks. Not very many foundations are still a relatively small community, but those people who have stopped to write textbooks, they tended to have been people in a more traditional realist mold. There's some efforts by people like Jeff Boob. He's written some good stuff, but there's a lot more that can be done educating younger physicists, and as well as I don't think that older physicists are necessarily changeable in their views as much, but we can put textbooks out there, and yes, popular things as well. I mean, I think there is scope to write sort of popular science books about these things, maybe even other resources like apps and games and things like that to do this kind of stuff. So I think you're definitely right about that, and there's a lot of work to be done, and I would definitely like to do some of that work in the future. So we'll see how it goes.
Good. Now we've been talking about future for a bit already. Here is a question about the future, also about making money for yourself. Let's imagine we set up a meeting 30 years from now. Now we look at the progresses in science. What's the chance that we would have discovered that quantum theory is wrong? I will ask you in your short answer to give a credence in percentage, and to give the amount of money you are willing to bet with each other. Matt, would you like to start?
I'm going to say it sort of depends, but I never say I think quantum mechanics won't be found wrong, but I'm not going to bet my house on it, right? I'll bet that. Yeah, I don't. I don't believe in precise amounts, but we would be in the sort of tens of dollars range. Yeah.
Interesting. Good. Markus, short answer.
Something like 20% would be my
Good.
Bayesian assignment of probability that quantum theory will be wrong. But if so, then in an interesting way and not in a, oh, it's actually classical sort of way.
How much money?
So if I get 5 times the amount I spent, well, I don't know, $100.
Good. Matt, if you'd like to elaborate.
Yeah, I mean, one of the reasons why I'm a bit, vague on this question is that I don't necessarily know that it's going to be obvious that quantum mechanics has been violated, right? So there are some obvious ways in which it can be violated, like if a spontaneous collapse theory turns out to be true, and we verify it, that's quantum mechanics was wrong. Okay, and for that I would bet a lot of money. Like if you make it more specific and you say, will spontaneous collapse theories be ruled out in my lifetime? I would say yes, definitely, and I would bet quite a lot of money on it. Right. But there are other things that could happen, like there are other things where it's not really obvious if it's a violation of quantum mechanics or not, or it's just sort of a generalization, right? So I'm going to give an example that there are people who have proposed in the context of string theory that you should have a non-associative algebra. So is a non-associative algebra of observables wrong? Saying quantum theory is wrong, because in quantum theories, all quantum theories and quantum field theories as we know it, the algebra of observables is associative. Is that saying that quantum theory is wrong? Other kinds of some modifications, if we turn out to have to modify the theory in an unexpected way in order to get quantum mechanics right, or quantum gravity right, but in some sense it's sort of still recognizable as the same theory. Some people might say, oh, we've shown quantum mechanics is wrong in that case, and other people might say, oh, that's just quantum mechanics, like in this context it has to be like that. So I'm if we're going to be, if we're very, very rigorous and say anything that's at all different from the way that we currently understand standard quantum mechanics, then I'd say the probability is quite high that it'll be wrong eventually. And I might give odds slightly higher than Marx's, like 30% or something like that. But if we're going to say, well, the whole physics community will have to agree that quantum mechanics has been violated, then it's much lower. I think it's tiny odds, because I think this kind of violation where it still sort of bears a family resemblance, a strong enough family resemblance that some people will still call it quantum theory, is probably the most likely outcome.
Markus, would you like to elaborate on your answer?
I mean, it's not that fruitful, I think, to speculate what the future will bring, but I find it extremely interesting and really fascinating to think about ways to test quantum theory and to try to make an educated guess about how it could eventually perhaps be violated. I'm not a fan so much of like collapse models and so on. I think if we find a deviation of quantum theory, then in the direction of even more weirdness, if you want. So then the question is, how can we test for this? And I think this is a practical research question. One thing we, at the moment, for example, we want to do is to say, like, how can we lift tests of Beck's version of contextuality, which in some sense say that a classical explanation is implausible, to a test of quantum theory, which would say that a quantum explanation is implausible. We just have single systems, so for this, for example. Or theoretically, what I find, I have a sort of favorite speculation that I like to work on. And the speculation is a bit like this. So suppose there's this underlying theory that some people call quantum gravity, but whatever it is, in some approximation, it gives you quantum theory and space and time as we know it, as a like smooth manifold and, according to GR and so on. Perhaps both of these theories don't apply to this fundamental level, whatever that fundamental theory is. And if that's the case, then you would expect that we see some shadow of this perhaps in the way that the two theories talk to each other. So, for example, we see that in some sense, quantum theory fits very well to relativity theory. Right? We have qubits. Qubits carry representations of the rotation group. And then we can have superpositions of spatial positions of particles without signaling and all these things. So you might say, if I want any theories of probabilities that fits into space and time, what properties must this theory have? And you can play the game to derive some properties of quantum theory from this. Right? And then ask, well, are there modifications that also fit into space and time? Quantum theory does, but maybe a few other beasts, maybe in the general probabilistic framework or more generally. And then you could speculate that perhaps they describe physics that you could find in some other regimes or so, right? This is all very speculative, but in addition to the fun and the fascination of the speculation, you can see that it can, in addition, shed also light on the structure of quantum theory and how it plays together with space and time, perhaps for some protocols or in some situations that you can use in other ways, right? But yeah, that's my way to speculate. I wouldn't want to bet money about what happens in 30 years. I'd rather take a pen and a piece of paper and try to ask, rotating a magnetic field in space, how can probabilities of detector kicks respond? So, yeah.
I mean, let me just follow up on that a little bit. I think that, the way to make progress here is you're right, is to find ways of testing quantum theory that are meaningful. One thing that I will say, though, is that we haven't always been very good at thinking about the actual, as opposed to sort of the information-y, probabilistically parts of things, we haven't always been very good at thinking about the real physicsy parts of things, because it's quite easy to propose ways in which quantum theory might be generalized. And then what people tend to do is say, well, let's go look for this effect. And then where do they look for it? They say, well, let's do a tabletop experiment with photons. And every time I see that, I kind of slap my forehead, because I'm like, well, usually you can say things like, well, if that effect appeared there with any kind of strength, all of classical optics would have to be wrong as well, right? Because the photons hardly interact with each other, and so you look for it in systems where quantum mechanics is already so vastly confirmed. It's ridiculous. So if quantum theory is going to break down or even get more weird in some way, you would expect it to happen in places where we don't really fully understand the physics right now. Maybe at high energy. I mean, it doesn't necessarily even have to be quantum gravity, because there are also issues with the unification of the other three forces. But, we need to do more to, you say, okay, there could be this effect. Could that effect actually help us solve another problem in physics? And if it can, what a reasonable physical system to look at where you might actually expect this effect to occur. It's very easy to rule out things that go beyond quantum mechanics by looking at systems which absolutely have to obey quantum mechanics based on our current evidence. So, I like the idea, Markus, you're talking about, of connecting things to space and time and perhaps gravity and things like that. I don't necessarily think that's the only way of doing it. We could look at, effects that occur in other high energy regimes, and also in condensed matter, potentially things that happen when you have collective degrees of freedom. We could look whether you might expect surprising things to occur there if quantum theory was generalized. But we shouldn't look, look at in regimes like, a few photons for effects where quantum mechanics is violated, because we're definitely not going to find it there.
Good. Yeah, I fully agree.
Good. So agreement. That's a perfect place to end. Thank you both very much for coming. We look forward to the reactions of the audience. Thank you.
And thank you very much for hosting this and inviting us on.
Yes, thank you, Ding, for doing this. Thanks for having us.